All right, we
Okay,
proceed with our afternoon session. So it's a great pleasure to introduce Kyoung-Seog Lee from University of Miami, who is going to tell us about complex surfaces with PG equal to zero. Kyoung-Seog?
yeah, thank you very much. So thank you, but first of all, I would like thanks to organizers for giving me this chance to this in this wonderful conference. Okay, so let me start. So today I will talk about the complex surfaces with the PG equal Q equal zero, and I will discuss three aspects of these surfaces. Yeah, and the last part is in very early stage, so I will say very sketch in a sketch way. But first two part I will begin with the history, and the first two part I will give more detail. So let me start. So first, let me begin with some classical history. So let me first fix some notation. So let S be a smooth projective surface of a complex number, and the PG in my notation, PG is the global number of global sections of canonical bundle, and this PM is M's plurality genera of my surface, and the Q is irregularity. So it's same as first cohomology of structure shift. And there's a very well-known rationality criterion of Castellubo that when S is a smooth projective surface with this second plurality genera and Q equals zero, then he proved that S is rational surface. And and then Marx Nether asked question that can we generalize this to, so when S is a smooth projective surface with PG equal Q equal zero, then he asked whether S is rational surface or not. And of course, the answer turned out to be wrong. So I don't know. What I mean is that there are lots of surfaces with PG equal Q equal zero, which is not rational, of course. So, and Nikke and Castellubo found some example, and later Godot and Campanelli found some surface of general type with PG equal Q equal zero. So there are many surface with PG equal Q equal zero, which is not rational. So let my S to be a smooth projective surface, complex surface with PG equal Q equal zero. Then by Enrique-Kodaira classification, we know that when Kodaira dimension is negative infinity, then it's rational surface. And when Kodaira dimension is zero, then it's birational to Enrique surface. And when Kodaira dimension is one, then just know that Q has an elliptic fibration over P1. So the typical example is Togashif surface. So let me just briefly call the construction. So when C1 and C2 are two smooth cubic curves in P2 meeting at 9 points transversally, and then I blow up these 9 points to make this surface into rational elliptic surface. And I take two smooth elliptic fiber and do logarithmic transformation of order P and order Q. Then I obtain surface so-called SPQ, and when S and P, P and Q are co-prime, then we know that this is a simply connected surface. So this is one typical example. And so for Kodaira dimension, anyway, negative infinity, 0 and 1, there are lots of study, but the surface of general type, it's still very mysterious area. So indeed, Mumford asked this question. So can a computer classify surfaces of general type with PG equal Q equal 0? So and let me briefly describe the current situation of classification of these surfaces. So first, from Bogomolov-Miyaoka-Yau inequality, we know that this k-scale should be from 1 to 9 for these surfaces. So let me consider this minimal surface of general type, and then let me assume that PG equal Q equal 0 and K scale is 9, then these surfaces are called the so-called fake projective plane. So the first example of these surfaces were found by Mumford. So he used so-called p-adic uniformization technique to obtain these surfaces. And all fake projective plane are rigid, and we know from a theorem Yao that all these arise from Bohr quotient. So recently fake projective plane are classified by work of Prasad, Jung, and Cartwright Steger. So they more or less classify this lattice. So I mean this all fake projective plane should arise from a Bohr quotient. And so this fundamental group it should be some arithmetic group. So and then they classify these gamma to classify fake projective plane, and they prove that there are exactly 100 fake projective plane. Okay, so for k-scale 9, the classification is done, and but let me mention that so because they classify these lattice, the actual geometry of fake projective plane is still quite mysterious. So so only how can I say we know how many fake projective plane, how many fake projective plane there are, but the actual geometry is still quite mysterious. And when I consider these surfaces with k scale equal 8, then these surfaces are called fake quadric. So then we can't apply uniformization here. So we don't know how to classify these surfaces, unfortunately, but there is a conjecture by Hitzbrich that when S is fake quadric, then the universal covering of S will be product of upper plane. So there's a conjecture, and we do not know whether this conjecture is true or not, but all example constructed so far arise in this way. So all examples so far has of this form, this product of two upper plane mod out this again arithmetic lattice gamma. And when gamma is reducible, then we call this surface, this fake quadric, or reducible fake quadric. And when gamma is irreducible, we call this fake quadric to be irreducible fake quadric. And recently, like the work of like the case of fake projective plane, there was some work by Stamvik and Linowitz, Stober, Boyd, and they studied possible list of irreducible gamma. And when gamma is reducible, then there's an algebraic geometric way to describe these surfaces. So reducible fake quadric has an ethyl covering of a product of two Riemann surface. So for reducible quadric case, there is some algebraic geometric description to describe these surfaces. So reducible fake quadrics are called surfaces isogenous to a higher product. And Bauer, Catanese, Grunwald, and Property classify these surfaces. And there are exactly 18 families of them. So, but irreducible surface is still, I think they study possible list of this gamma, but I think, because we do not know the Hitzbrich conjecture yet, so I think the classification is still far. Okay, so is there any question so far? Okay, if not, let me go further. So we know there are certain classification for k-scale 9 and k-scale 8, but from k-scale 7, the minimal surface, from K-scale 7, there's no uniform way to attack classification problem. So indeed, for K-scale 7 case, there are really few examples. So for a long time, the only known example is the family constructed by Inoue. So Inoue constructed the surface by, so he considered product of 4 elliptic curves and with natural finite group action. So, and he considered some complete intersection inside this product of 4 elliptic curve. And then he and then he constructed Inoue surface. So this is smooth projective surface with K-scale 7 as precaution of this complete intersection. So this has been a very for a long time these surfaces are only example, but recently Ipan Chen construct another family of minimal surface of general type with K-scale 7, and he constructed certain weak Derived surface of degree 1, and he considered some weak Derived surface degree 1, and he considered some bi-double covering of some the singular surface to obtain minimal surface of general type with the K-scale 7. So, and also one other famous example is so-called Barney surfaces. So Barney surfaces, Barney consider some configuration of 9 lines in P2 and consider bi-double covering of these 9 lines. So he constructed the surface of general type from K-scale from 2 to 6. And Kum and Nae also consider some kind of double covering of Enrique surface and construct the surface from K-scale from 1 to 4. And Bao and Cataneza generalized this construction and obtain some. So what I mean is what Kum and Nae constructed are some closed subfamily in this Bao-Catanese 6-dimensional family. So Bao-Catanese generalized this construction to obtain some bigger space. So and so let me give you several more examples and go to. So there are one other very well studied family. So when let G be a finite group and C and D be algebraic curve with G action, and then I consider diagonal action of G on this C times D, and on algebraic surface, so I consider this C times D and diagonal G action on this surface, and I consider this quotient of G action, and then consider minimal resolution. So this is so-called the product quotient surface, and this also this surface provide lots of very nice example of these surfaces, and they provide lots of new fundamental group for surface of general type with PG equal Q equal 0. And let me. There are so many players here, but let me finish introducing player by this saying this section. So, but what I mean in general, what I mean is that in general, it's very hard to find examples of simply connected surface of general type with PG equal Q equal 0. So very long time, for a very long time, the so-called Barlow surface is the only known example of surface of general type with PG equal Q equal 0 and K scale 1. So simply connected. So let me explain how she constructed her example. So she considered the simply connected surface with K scale 10 and PG equal 4 with certain D5 action. So D5 is diagonal group of order 10. And then she consider this again take quotient of this surface and consider minimal resolution. And she proved that these surface satisfying this condition. So in 1985, this was first example of surface of general type with PG equal Q equal 0 and simply connected. And recently, Lee and Park use Yonglam Lee and Jong-il Park use so-called Kugo-Einstein smoothing technique to construct new examples of simply connected minimal surface of general type. So their construction is in a way they construct a certain singular rational surface and prove that these surface admit Kugo-Einstein smoothing, and so they obtain, by this technique, they obtain new example of simply connected surface of general type. And via similar way, Lee and Park and Sin, so they construct lots of example of new examples of simply connected minimal surface of general type. Okay, so let me finish to introducing players here. So, but what I want to say is that there are no uniform way of constructing example. So as you see, there are many techniques, and so far there is no uniform way to understand how we can construct example. So most standard technique is, of course, taking quotient or taking covering or this Kugo-Einstein smoothing, but there's no guarantee that these are all techniques one can expect, and there are might be many more new example to come. Okay, so so why these surfaces are interesting? So let me briefly recall some of history of these surfaces. So let S be simply connected, compact-oriented smooth form manifold. Then a very famous theorem of Friedman tell me the quadratic form, intersection form determine topological type of S. So in other words, when S and S prime be two simply connected compact-oriented smooth form manifold whose intersection forms are equivalent, then he proved that the S and S prime are homeomorphic to each other. So then, as we discussed, for example, Togashif surface, when you take multiplicity 2 and multiplicity 3 logarithmic, order 2 and order 3 logarithmic transformation, and the Barlow surface we discussed, and Lee-Fox surface and the other example we discussed previous slide are all homeomorphic to some rational surface. So of course, these surfaces are not biholomorphic to rational surface because their Goodyear dimensions are different. But anyway, in topological level, they are the same. So then how can we distinguish these surfaces? Of course, we can distinguish its complex structure, but Donaldson actually used Yang-Mills theory. So in mid-1980s, Donaldson used Yang-Mills theory to study smooth structure of form manifold. And these technique will apply to study smooth structure of previous example. So let us briefly recall his construction. So let E be a SU bundle with whose second Chern class is 1. And let TA be a connection on E and FA be its curvature. Then I consider this infinity dimensional space of gauge equivalence classes of connections on E, and let B star be dense open subset of irreducible connection. So for each Riemannian metric G, there is a moduli space defined by, and this moduli space has expected dimension of this case. So in this case, this is 2 because C2 is 1 and C1 scale is 0. So in this case, this is two-dimensional, real two-dimensional space. And so what I mean, this moduli space is the set of connections satisfying this ASD equation. And then he considered this fundamental class of this moduli space, and he defined a smooth invariant in this way. So let me assume that this S times B star have irreducible or a universal family. And then I consider this fundamental class of this moduli space, and let me call this M. And then I take this slant product. So I have a map from, so whenever I have a class here, then I obtain some class in the second cohomology class of S. So in this way, he obtained new smooth invariant. And he also showed that this moduli space of ASD connection on my vector bundle can be identified with the moduli space of stable bundles whose determinant is trivial and having the same second Chern class. So anyway, and he introduced this new invariant and proved that these invariants should satisfy this condition. So when S is close oriented, simply connected for manifold with this this positive eigenvalue of second cohomology is 1. Number of positive eigenvalue is 1. Then and I consider some chamber in a positive cone of this second cohomology class of S. And then this invariant gives a map from this chamber to second cohomology of S and satisfying this condition. So and using this invariant, Donaldson proved that this Togashif surface has different smooth structure with rational surface. So to be more precise, he showed that this ASD moduli space on Togashif surface can be identified with the multiple fiber with multiplicity 2, but the moduli space on rational elliptic surface is empty. So using this fact and using this invariant, he proved that two complex surface, rational elliptic surface and Togashif surface are not diffeomorphic to each other. So the above result was further generalized by two groups. So two Friedman and Morgan and O'Connell and Van de Ven. So the two Togashif surface with S2Q1 and S2Q2 are diffeomorphic to each other if and only if Q1 and Q2 are the same. So as a corollary, we can show that the blow up of P2 and 9 points has infinitely many smooth structure. So so and then after that there has been lots of work studying complex surface from gauge theoretic perspective, and it turns out that the complex structure and smooth structure for manifold are very closely related. For example, Friedman and Morgan proved that for compact oriented smooth for manifold, there are only a finite number of algebraic structure up to deformation, and more important, more closely related to this talk, when S so Friedman and Morgan and Friedman and Kin and O'Connell and Telemann proved that when S and S prime be two smooth projective surfaces which are diffeomorphic to each other, and when S is rational, then they prove that S prime is also rational. So so in some sense, rationality can be seen by looking at smooth structure of underlying four manifold. And Brisse and Duo and Friedman, Morgan and Friedman Kin also prove that the plurigenera of smooth projective surface and Godaira dimension are diffeomorphic in differential smooth invariant. So okay, so is there any question so far? Okay, if not, let me keep going. So Yeah, now we have many examples of surfaces of general surfaces with PG equal Q equal 0. And yeah, there have been lots of study of their fundamental group, moduli space, zero cycles, and other things. But the problem here is that we are still very far from the classification of these surfaces. So yeah, for example, even fake quadratic, we do not have any classification. Even there's no strategy to how we can approach this problem. So in this sense, it's desirable to find several new points of view to understand them. So a natural question might be, what kind of common properties these surfaces can have? So what kind of, so if these surfaces have some common property, then I might study these common surfaces, having possible surfaces having this common property and try to classify these surfaces. So I want to find some kind of pattern of these surfaces. As you saw before, so for example, for surface of general type with PG equal Q equal 0, there's no easily seen pattern. So it's a little mysterious what kind of common property they might have. Of course, there are some kind of common property, expected common property, but yeah, but still very far. One obvious common property is something like this. So intersection form, when I consider this intersection form, then this intersection form has signature 1, B2 minus 1. So this is one obvious common property, but anyway, so, and then we can say that when S is a simply connected smooth projective surface, then anyway, it is homeomorphic to rational surface. So yeah, this is one common property, but and there are some other expected common property, but yeah, I want to find some more common property to attack this classification problem. So, and let me remark that all expected common property I will discuss today were first observed for rational surface and all related to study certain curves, certain classes of curve in these surfaces. So let me first discuss some birational geometric aspect of these surfaces. So let me first recall some terminology. So Hu and Q studied relation between minimal model program and variation of GIT, and they defined the notion of a Mori dream space as follows. So variety X is a Mori dream space if X is cube factorial variety and the first cohomology of structure shift is trivial. And the nav cone of X is convex cone generated by finitely many semi-ample classes. And there are finitely many birational maps from X to Xi, which are isomorphic in codimension 1, and the Xi are variety satisfying. These target variety Xi are variety satisfying the first two conditions. And if these are movable divisor, then there's on index I and the semi-ample divisor di on Xi such that D is a pullback of this di, semi-ample divisor. So if these conditions satisfy, then they call this space as a Mori dream space, and as name suggested, so this surface has very nice birational geometric property. So yeah, and so this being Mori dream space can be understood in other way. So when X is a normal projective Q factorial variety with a finitely generated class group, and then let gamma be a subgroup such that the class map from this value divisor to this DA divisor induce an isomorphism when we tensor Q. Then I define my Cox ring to be this collection of all some gamma graded multi-section ring defined in this way. So that means intuitively, this means that I consider all line bundle on my space, and then consider all section, and then this says that there is some way to make this ring to be a grade ring. So this is not 100% precise description of this Cox ring, but intuitively, anyway, this the way to understand Cox ring is consider all line bundles on my variety and consider all sections there and consider this graded ring. And Hu and Kier prove that the X is Mori-Dream space if and only if this Cox ring is finitely generated. So, yeah. So when X is Q factorial variety such that my Picard group is finitely generated abelian group, then being Mori-Dream space is equivalent to that this Cox ring is finitely generated ring. So, yeah, and there's one remark here, because in my previous definition, the notion of Cox ring depends on the choice of this lattice in Bayes divisor class, but this finite generation of Cox ring does not depend on the choice of this lattice in Bayes divisor group. So yeah, it doesn't depend. So, and even more, there's a way to define a canonical Cox ring introduced by Hausen, but let me skip this part. So anyway, there's one way to, well, there's a way to define a natural, Cox ring, but yeah, anyway, or this, anyway, for being Mori-Dream space, finite generation of one of these Cox rings is enough. So for surface case, the criterion of being Mori-Dream space is rather simple. So let me recall a theorem of Artebani, Hausen, and Laplace. So when X is a Q factorial projective surface with a finitely generated divisor class group, then this being Mori-Dream space, or equivalently Cox ring is finitely generated, is equivalent to the effective cone is a rational polyhedral cone, and the semi-NEP divisor is same as semi-ample divisor. So there's very simple criterion for being Mori-Dream space in for surface case. And there are many examples of surface with non-positive Kodaira dimension, which are Mori-Dream space. For example, when the Kodaira dimension is negative infinity, there is well-known theorem by BCHM. So when X is a log Fano variety, then X is Mori-Dream space. So for example, all depth edge surface are Mori-Dream space. So so for surface with the negative Kodaira dimension, then there's a well-known criterion. And when Kodaira dimension is trivial, then again the Artebani, Hausen, Laplace prove that when X is K3 or NK, then X is a Mori-Dream space if and only if this automorphism group is finite group. So Kodaira dimension negative infinity and zero case, it's quite well established. There's quite well established history, but for surface of general type or Togashif surface, there's not many things seems to be known. So as we saw, there are some similarity between the surface of general type or Togashif surface with this rational surface. So one might ask that when I consider a minimal surface of general type with PG equal Q equal 0, then the following question seems to be natural. So I mean, this effective cone, when the effective cone is rational polyhedral cone, and when the NEP cone and semi-ample cones of X are the same, and moreover when X is Mori-Dream space. So the following question seems to be quite natural. And what Kum and I prove is that the following, so we gave a list of classical known surfaces which are Mori-Dream space. So the following minimal surface of general type with PG equal Q equal 0 are Mori-Dream space. And moreover, we compute their effective cone very explicitly. So for example, fake projective planes, yeah, this case is trivial. And so the surface isogenous to higher product of a mixed type, and the inner surface, and the surface constructed by Ifan Chen, which I told you, and the Barney surfaces with the k-scale from 2 to 6, and the product quotient surfaces, and a family of Kumnai surface. So we found new examples of Mori-Dream. So examples of Mori-Dream spaces of general type with PG equal Q equal 0. So there are some, yeah. So many, I discussed this result with many experts, and there are many opinions about this. So some experts told me these being Mori-Dream is rather special for the surface of general type with PG equal Q equal 0. But we still could not find any minimal surface of general type which is not Mori-Dream space. So yeah, this will be quite interesting question. But in this context, minimality condition is rather important. So for example, I can construct certain surfaces of general. So let me describe this way. I consider certain family of Kumnai surfaces, and if I blow up 8 points there, then yeah, I can prove that. So I can prove that these surfaces are not Mori-Dream space. So as I told you, Kum and Nai constructed so-called Kumnai surfaces from taking from this Enriquez surface, and I choose some specific Enriquez surface, and then take this double covering, and then we can prove that these surfaces are not Mori-Dream space, but these surfaces are not minimal surfaces. So if I consider non-minimal surfaces with PG equal Q equal 0, then it's, one can find, examples of non-Mori-Dream spaces. And let me give one remark that if we blow up 9 point in general position in P2, then the surface we obtain is not Mori-Dream space. So yeah, there are some similarity happen for this minimal surface of general type in the Derived surface here. So, okay. And it seems to be an interesting and important task to classify Mori-Dream surface of general type. Why this is important? Because if one can prove that all surfaces of minimal surface of general type with PG equal Q equal 0 are Mori-Dream space, then there are very well developed birational geometry for these surfaces. So I have some way of systematic understanding of surface of general type. As I told you, there's no systematic way to study these surfaces. So if I can classify all Mori-Dream spaces or surface of general type with PG equal Q equal 0, then anyway, I have a certain class of surface of general type, which I can have a systematic understanding. So yeah, in this sense, to understand these surfaces, to classify these surfaces are very important. And so the first test case, as I told you, fake projective plane are trivial case, but from fake quadric, it become non-trivial. Certainly it become non-trivial test case. So let me consider the fake quadric. So, and I consider this fake quadric. So let me recall that this is some kind of a general type surface analogy of P1 times P1. It's not homeomorphic to P1 times P1, so because it's not simply connected, but in birational geometry level, in Picard group level, when I see this Picard lattice, then this is similar to this P1 times P1. So we can naturally ask that, okay, then is this effective cone is rational polyhedral cone, and is snap cone is same as semi-ample cone? And what I and Davide property prove is that when I have a reducible fake quadric, then this is Mori-Dream space. and this effective cone and semi-empty core are the same. So when you see the actual construction of these surfaces, then it's rather, yeah, it's not easy. It's not obvious that these surfaces having these properties, but we prove that this is true for reducible fake quadratic. But for irreducible fake quadratic, like fake projective plane, the study of irreducible fake quadratic is quite difficult. So we need some other technique to attack this problem for irreducible fake quadratic. Okay. So, and then the natural question might be, is there an example of Mori-Dream Togashif surface or a numerical Godot surface? We couldn't find the example of Mori-Dream surface with this type. And anyway, the most important question might be classify the minimal surface of general type with PG equal Q equal 0, which are Mori-Dream spaces. Okay, so is there any question so far?
Wait, I'm a little bit lost. Do you conjecture that all the minimal ones are Mori dream spaces or not?
So, yeah, thank you for the question. Indeed, what I mean is that I met some, to be honest, I have no opinion. I couldn't find any example, non-example. So, and I met some experts that irreducible fake quadratic will be the first kind of counterexample for these surfaces. So being non-Mori-Dream minimal surface of general type. So, and also I met some experts that when k-scale is 1, because when k-scale becomes smaller and smaller, then this Picard group become bigger and bigger. So the problem is really complicated when Picard group become bigger and bigger. So k-scale equal 1 or irreducible fake quadratic can be the first example, which is minimal surface of general type with PG equal Q equal 0, which is not Mori-Dream space. But to be honest, I have no opinion so far. I just yeah. So
okay, thank you.
Yeah, thank you. But what I can say is that if all these surfaces are Mori-Dream space, then I have a way to, how can I say, systematic understanding of these surfaces. Okay, thank you very much. So, and yeah, let me skip this slide. So I just yeah. So this surface gives me a example of yeah some historical conjecture in algebraic theory of algebraic surfaces. Okay, then let me begin to discuss the derived category of coherent shapes on algebraic surfaces. So because I'm little running over time, let me briefly let me skip the definition. So derived category of coherent shapes is very one of the most important invariant in algebraic geometry, and so it's so the definition of this invariant is as follow. And when so this is then but this is the most important, one of the most important invariant in algebraic geometry, but it's quite hard to deal with these invariant. So how can we describe for when I consider this some complex surface with PG equal Q equal 0, then the natural question will be, how can we describe the derived category of my surface? And then the natural way to study this derived category of surfaces is to construct the so-called semi-orthogonal decomposition. So a semi-orthogonal decomposition of a triangulated category is to divide my triangulated category into smaller pieces, satisfying there's no home from AI to AJ, where AI belongs to this large AI and AJ, small AJ belongs to a big AJ with this I greater than J. So there's no arrow from back to forth. So this is the first condition. And second condition is that these small category generate the whole triangulated category. When these conditions satisfy, then I say that my triangulated category has semi-orthogonal decomposition. And this can be, anyway, this is very powerful tool to understand the geometry, so some derived category of algebraic variety. And the classical way to construct semi-orthogonal decomposition is to use so-called exceptional collection. So an exceptional object of a triangulated category is an object satisfying the home from E to E surface C and home from E to E shifted by K for any non-trivial K is 0. And when I construct, then I consider a sequence of exceptional objects. This is called exceptional collection. And I call this sequence of exceptional objects to be an exceptional collection if, the home from, again, the same condition. Though there's no home from back to forth, then I will call this sequence of exceptional object to be exceptional collection. So when I have this exceptional collection, then I always can make semi-orthogonal decomposition. And these previous AI is generated by one exceptional object. And so category generated by an exceptional object is equivalent to derived category of point. And for surface of surface with PG equal Q equals 0, then any line boundary is an exceptional object. And from Orloff's blow-up formula, we can see that any rational surface has full exceptional collection consisting of line boundary. So there's again one pattern from rational surface. So from this Orloff's blow-up formula, we have that any rational surface has exceptional collection of line bundle and it's full. It means that the exceptional collection generates the whole derived category. So what happened for other surface with PG equals 0, Q equals 0? So let S be a classical Godot surface. Then Bochning, Bosma, Sosna proved that there is an exceptional collection of line bundle of length 11 on S. So this is maximal possible length of this derived category of S can have. And let S be the full triangulated category generated by these exceptional collection and A be the orthogonal complement of A. Then they prove that the gross-centric group of A is Torsion group of order 5, and the Hochschild homology of A is trivial. So means that so this is a new type of category which haven't been observed before. So there's name for this category. So when S is smooth projective variety and A is an admissible subcategory of derived category of X, then I call A to be H phantom if Hochschild homology of A vanishes. And I will call this quasi-phantom if Hochschild homology of A vanishes and gross-centric group is finite. And I will call this phantom if gross-centric group of A is also vanishes. Okay, so after their work, there have been lots of work studying surfaces of general type. And so for many surfaces, the same pattern happen. So I can construct the exceptional collection of maximal length. And then the orthogonal complement is not trivial. So for example, fake projective plane and some fake quadri and Kulikov surface, Barney surfaces, and determinant Barov surface. Many people observe the same pattern happen. So we have many examples now, but the problem is the structure of phantom category is still very mysterious. We know some example. So let me tell you some example, some property observed so far. First, by theorem of Orloff, Bondar and Orloff, the derived category of S determined S when Ks is ample. And so and the second, as I told you, this existence of phantom is very a new phenomena. So many people were very surprised, and it was not expected before. And for many cases, the category generated by exceptional collection. So as I told you, the phantom category is orthogonal complement of exceptional collection. So, and this category generated by exceptional collection are deformation invariant. In many cases, this is true. And so in some sense, as by the first line, the derived category of S determine the surface itself, but this category generated by exceptional collection is deformation invariant. So in some sense, this phantom category somewhat determine the category variety itself. So the force property reflects that kind of property. So for some cases, we can compute the second Hochschild cohomology group of this phantom category, and they coincide with the deformation of complex structure. So they might be think as something like totally invariant in this case. And for some cases, we can explicitly construct object in phantom category, but for many cases, this is not sufficient. What I mean is that we can construct some example, but usually it's not enough to say whole category. So there are some more example. For example, there are phantom category in Togashif surface. So as I told you, using Kyoung-Seog Lee smoothing technique, Urjua and Cho and Lee constructed example of the Togashif surface from this Kyoung-Seog Lee smoothing technique. And Cho and Lee proved that there are exceptional collection of length 12 on this Togashif surface. And so there is phantom there. And also Cho proved that via similar idea for generic Enrique surface obtained via this Kyoung-Seog Lee smoothing, then the blow up of this Enrique surface has exceptional collection of length 13. So this is again quite new phenomena. So, but yeah, so again, we have many examples, but still the structure is very not clear. And my personal, maybe it's a general opinion, but it's not, I think it's hard to find literature explicitly written this, but maybe, anyway, the general expectation is that there will be a phantom category in derived category of simply connected surface with PG equal Q equal 0 with non-negative Kodaira dimension. And for rational surface with a small Picard group, then because this is Fano, then one might expect that there's no phantom in this derived category, like some other examples. And recently, Pirochkov obtained the following very surprising result, that there's, this very nice result. So there's no phantom subcategory in the derived category of the Derived surface. So this expectation is somewhat true in the Derived surface case. And so, but still the structure is quite mysterious. So, okay, so any question so far? So in any case, let me summarize. So it seems that the three topics we discussed, so three topics today. So first, gauge theory, and the second, this birational geometry of these surfaces, and third, derived category. But it seems that there are some interaction between these three topics. So let me explain. So first, when you see the literature of gauge theory, many computation of Donaldson invariant reduced to find certain semi-ample divisor having certain property. For example, when you see the paper of Friedman and Kim, then many problem reduced to find certain semi-ample divisor whose contraction having only rational surface singularity or elliptic singularity. So when we know a surface is a Moridian space, then we can, indeed, in our previous example, we can say everything, that we can find all contractions and all contractions of my surface to a normal surfaces and the vibration of these surfaces. So what I mean is that because we know the Mori-Dream space, the birational geometry of the surface is controlled in very combinatorial way. So I can control this birational geometry very well. So this semi-ample divisor so I can say that whether this surface has certain semi-ample divisor or not. And moreover, when one tries to describe this modularized ASD modularized space in gauge theory, then the problem often leads to find certain base locus of certain linear system. And also it's again related to this birational geometric property of this surface. So yeah, for being Mori-Dream space really help to have some systematic understanding to describe this moduli space or compute this Donaldson invariant. And also if one is trying to construct the exceptional collection of maximal lengths in derived category of surface, then knowing its effective and F-con is very useful. Indeed, this is our original motivation to study Mori-Dream space of general type. Okay, and when we concentrate on the semi-orthogonal decomposition of surface with PG equal Q equal 0, then it seems that two important tasks is to understand structure of quasi-phantom category and to study the following conjecture of Orloff. So Orloff, I think, Orloff made the following conjecture: when S is surface with PG equal Q equal 0, and if S has a full exceptional collection, then it's rational. So then, of course, as I told you, the rational surface has full exceptional collection, but this not. Sorry, I forgot to write rational here. But anyway, this so this doesn't get but having full exceptional collection does not guarantee that it doesn't have a phantom. So this conjecture, I think, is still open, and there are several evidence for this conjecture. For example, we will have a talk by Barat tomorrow, and also there's a theorem by Brown and Shipman that when S has full strongly exceptional collection of line bundle, then it's rational. So we have some supporting conjecture. And so it seems that the existence of phantom is closely related to rationality, as we discussed, because in rational surface, no phantom observed so far. And I don't know, maybe it's as far as I know. And please recall that the rationality can be detected by looking at smooth structure of underlying Form by the following result. So the natural question arises in this context would be, can you use gauge theory to study Orloff conjecture, and can you understand phantom category via gauge theory? And I and Professor Kacharkov and also partly with Atansha Shimani, we studied this conjecture, this thing. So we discussed this gauges when we consider this gauge theory or modularized space. Many modularized space in gauge theory can be understood as some modularized space of stable bundle with fixed Chant class. For example, this ASD modularized space can be identified with modularized space of vector bundles. So let me assume that there is a universal bundle E on this S times M, and we can consider this pre-Mukai transform. So recently there are some works in this direction, so interaction between moduli space and original variety, and for curve case, this is quite, there have been some study in curve case, and surface case, it's still, I think, very new. So the way I'm considering with Kacharkov, Professor Kacharkov, is to use this pre-Mukai transform to attack this Orloff conjecture. So one way to prove this Orloff conjecture is that I consider this image, pre-Mukai image of my moduli space to the derived category of surfaces having exceptional collection of line bundle. Then if one can prove that this image doesn't lie on this category generated by exceptional collection, then one can say that this exceptional collection cannot be full. So this is one strategy we have to prove certain exceptional collection of line bundle is not full. And we are investigating some of the example we have to check this this conjecture, and we have some heuristic argument, but we still couldn't finish this so far. So let me mention this. And one more interesting question on my is natural is that so this this ASD moduli space is curved as I discussed. So then there's natural pre-Mukai transform from derived category to this moduli space. And there's some hope that we can describe the image of phantom in the moduli space here. Okay, so thank you very much. Sorry for over time. So and thank you very much for listening.
All right. Any questions?
What is the motivation for your conjecture about the image not being contained in the?
So our motivation is comes from, for example, considering Togashif surface. So when I consider this Togashif surface, then as I told you, the moduli space there are two types of moduli space. So one is which Donaldson consider, and one is the so-called SO3 moduli space. Anyway, so both corresponding to this multiple fiber. So then we can, so what I mean is that, so if this all image belongs to the exceptional collection of line bundle, then I can prove that. So what I mean is that all this, so what I mean is that so let me briefly, let me be quite rough explanation. So this skyscraper shape of this multiple fiber corresponds to this vector bundle. So this image of, so what I mean is that because this is phantom, so when I consider this all skyscraper shape on this Togashif surface, then some of skyscraper shape should lie in, should have non-trivial image in phantom. And this image of vector bundle is more or less determined by this skyscraper shape on this multiple fiber. So that's one reason we have this conjecture. And the other reason is that we can compare this deformation of this elliptic curve and the deformation of this surface. And we can construct a map from this deformation of this elliptic surface to this elliptic curve to deformation of this Togashif surface. And obviously for the case of Cho and Lee, the image of deformation doesn't lie on this this normal Hochschild cohomology constructed by Kuznetsov. So that's the reason we have this type of expectation. And when you consider several more examples, then there might be some other type of that means that. So again, something like, and also we consider Barlow surface, then but we couldn't finish that analysis for that case. So let me just mention Togashif surface. So is this answer your question?
Okay. Yeah, thank you.
Yeah, thank you.
Other questions? If not, let's thank Kyoung-Seog again. And so we'll proceed at 5 p.m. New York time.
Okay. Thank you very much.